Hello everyone. I am here to discuss about a few applications of op amp. Okay, first we will see what is an op amp. An operational amplifier is an integrated circuit that can amplify weak electric signals. Operation amplifiers is also known as op amps, are basically a voltage amplifying device designed to be used with components like capacitors and resistors between its in and out terminals. They are essentially a core part of analog devices. Feedback components like these are used to determine the operation of the amplifier. The this operation amplifier has many applications in which first we will see about simple arithmetic circuits and about op amps generating a square wave, which is also known as astable multi-vibrator. Okay, let's see what are the subtopics are there in arithmetic operations. It is addition, subtractor, differentiator, integrator, log and anti-log circuits. The main important point is this arithmetic is only for output voltage. For example, in this adder circuit, this is the adder circuit. In this adder circuit, this op amp adds the both input voltages and gives us output voltage. For this application, we would use a op amp. Let's see the derivation. Okay, first we can see that I is equal to I1 plus I2 from this circuit. Then here VB is grounded. Here VB is grounded. So VB is equal to 0. And then VA is equal to VB. Hence VB is 0. VA is also 0. Okay, applying KVL on first voltage, that I1 is equal to V1 minus VA divided by R1. We know that VA is equal to 0, so V1 by R1. Next, I2 is equal to V2 minus VA by R2 is equal to VA is equal to 0, then V2 by R2. We know that I is equal to I1 plus I2. Therefore, I is equal to V1 by R1 plus V2 by R2. This is the I. At output end, I is equal to VA minus V0 by RF. All we are using KVL only. I is equal to VA is equal to 0 minus V0 by RF. We know that I is equal to I is equal to V1 by R1 plus V2 by R2 equal to minus V0 by RF. V0 is equal to minus RF by R1 into V1 plus RF by R2 into V2. This is actually the output voltage. If RF is equal to R1 is equal to R2, then V0 will become my negative of V1 plus V2. In the circuit, the output voltage gives the differences between input voltage V1 and V2. Okay, let's take at node 1. At node 1, V2 minus V by R1 is equal to V minus V0 by RF. Simply dividing the denominator, V2 by R1 minus V by R1 is equal to V by RF by V0 by RF. From this we can calculate V0. V0 is equal to V by RF plus V by R1 minus V2 by R1. In other terms, we can write V0 as V by RF plus V minus V2 by R1. By taking common, V0 is equal to RF by R1 into V minus V2 plus V. Finally, V0 is equal to 1 plus RF by R1 into V minus RF by R1 into V2. This can be equation 1. Let us consider at node 2. At node 2, V1 minus V dash by R2 is equal to V dash minus 0 by R3. From this we can identify V dash is equal to V1 into R3 by R2 plus R3. This can be equation number 2. From equation number 1 and 2, V0 can be written as V0 is equal to 1 plus RF by R1 into R3 by R3 plus R4 into V1 minus RF by R1 into V2. By simplifying it, V0 is equal to RF by R1 into 1 plus R1 by RF divided by 1 plus R2 by R3 into V1 minus RF by R1 into V1. This is the equation number 3. When V1 is equal to V2 is equal to 0, then V0 will be 0 volts. Sorry, this is V2. Okay. This condition will be satisfied only when R1 by RF which is equal to R2 by R3. Then equation 3 becomes V0 is equal to RF by R1 into V2 minus RF by R1 into V1. By taking common, V0 is equal to RF by R1 into V2 minus V1. If RF is equal to R1, hence the output voltage becomes V2 minus V1. Okay, this is the final subtractor. Now we will see the differentiator amplifier circuit. At first, from the circuit we can analyze that given that VB is 0. As we already know that VA is equal to VB. When VB is 0, VA is also going to be 0. Okay, let's see at input. At input stage, the current I is equal to C into d by dt into V in minus VA. As we know that VA is equal to 0, the current becomes I is equal to C into d by dt into V in. Let's take this as equation number 1. At output, I is equal to VA minus V naught by RF, as VA is equal to 0 minus V naught by RF. We know that I is equal to, substituting I in this, we can know that C into dVn by dt is equal to minus V naught by RF. From this, V naught is equal to minus C into RF dVn by dt. This is the output voltage. Now let's see the integrated circuit. As we see in the previous circuits, here also VB is equal to 0. Hence VB is equal to 0, VA is also going to be 0. In input side, I is equal to Vn minus Va divided by R1. Hence Va is equal to 0, I becomes Vn by R1. This can be first equation. In output side, I is equal to Cf into d by dt Va by V naught. We know that Va is equal to 0, only V naught is present. The negative comes before Cf. I is equal to minus Cf into dV naught by dt. From this, Vn by R1 is equal to, applying the I value in here, Vn by R1 is equal to minus Cf into dV naught by dt. Integrating with respect to t, integral 0 to t Vn divided by R1 dt is equal to minus Cf integral 0 to t d by dt of V naught into dt. Hence the integral and differentiation cancels each other. Then the final V naught is equal to minus 1 by R1 Cf integral 0 to t Vn into dt. This is the final output voltage of integral circuit. Let's see the logarithmic amplifier circuit. Firstly, by applying KCL at node A, we will get to know the value of IR. IR is equal to Vn by R. By the voltage current relationship, we can find IC is equal to IS into e power VBE by VT. By taking natural log, ln IC by IS is equal to VBE by VT. From the circuit, we can easily see that by KVL, minus VBE minus V naught is equal to 0. Hence V naught is equal to minus VBE. Hence substituting the V naught value in VBE, V naught will be minus VT ln IC by IS. This output voltage in logarithmic amplifier circuit. And then we see anti-log amplifier circuit. The same rule, applying KVL, Vin minus VEB is equal to 0. Then Vin is equal to VEB. Applying KCL at node A, IC is equal to IR. IC is equal to 0 minus V naught by R. Then IC is equal to minus V naught by R. From this we can easily know that V naught is equal to minus R into IC. IC is nothing but IS into e power Vin by Vt. Hence substituting this in V naught, we will get the output voltage. Okay, now let us see about square wave generator. It is known as the astable multi-vibrator or a free running oscillator. It's look like a comparator with hysteresis, that means Smith trigger circuit, except that the input voltage is replaced by a capacitor. The circuit has a time dependent elements such as resistance and capacitance to set the frequency of oscillation. For simpler understanding, I have mentioned the color yellow for capacitance reaction and the V naught output of the this generator as red color. When the capacitance gets charged, V naught the curve V naught is remains constant at V sat. When the capacitance gets discharged, the curve V naught moves plus V sat to minus V sat. Again, when the capacitor gets charged, the curve V naught moves from minus V sat to plus V sat. Hence, this oscillations take continuously to generate a square wave or rectangular wave. The equations involved this astable multivibrator are written here. Mainly, the voltage across capacitor is Vmax plus Vin minus Vmax into e power minus t by Rc, and the T1 is equal to Rc ln 1 plus beta by 1 minus beta. The total time is 2 times of T1, and the very important factor is frequency in which the capacitance is charging and discharging, and the output voltage peak to peak will be 2 times of Vsat. Okay, that's all in this video. Hope you enjoyed it and liked it. Thank you.